Hello everybody, and welcome to the beginning of section 5.5. We're looking at page 13 of our workbook. We're going to start this section off by trying to calculate the integral of 2 over x minus 1 times x plus 1. To do this integral, we need a genuinely new integration technique called partial fractions. Okay, the way partial fractions work is it takes a function like this and breaks it into smaller parts that are easier to integrate. Okay, and let me show you what I mean. So I'm going to start by just not worrying about the integral and just looking at the function on the inside. 2 over x minus 1 times x plus 1. The technique of partial fractions is kind of like the reverse of finding a common denominator. We're going to take this fraction and we're going to break it into smaller pieces. Okay, so we're going to take that denominator, x minus 1, x plus 1, break it into two parts. Turns out we can find constants a and b that make this a true statement. Okay, we need to figure out what those constants are though. So what we're going to do is some algebra here. So what I'd like to do is to multiply both sides of this equation by the denominator on the left-hand side. Okay, x minus 1 times x plus 1. We can do that as long as we do the same thing to both sides. Okay, and over on the left, notice what happens if we do that. If we multiply by x minus 1, x plus 1, that whole denominator is going to cancel. That was kind of the point for multiplying by the denominator. Okay, so we've just got a 2 left over on the left-hand side of the equation. And what happens over on the right-hand side? Okay, well there, we have two terms, and so we actually have to distribute this x minus 1 times x plus 1 and multiply it by both of the fractions that we see. Okay, so let's start by noting that on the left-hand side of the equation, everything is canceled except for the 2. So we've just got a 2 over there. And what happens on the right? Well, let's take it one term at a time. If we start with the a over x minus 1, it's going to get multiplied by x minus 1, x plus 1, and what cancels is just the x minus 1. Okay, and so what would be left over for the first term is just the a that's in the top times the x plus 1. Okay, and we're done with the first term. Okay, clear a little clutter away here. Okay, and I'm just going to rewrite the x minus 1, x plus 1 so we can start again. We're now ready for the second term here. So what happens if you take b over x plus 1 and multiply it by x minus 1, x plus 1? Well, this time, the x plus 1's cancel, and we're left with just b times x minus 1. Okay? So there's what everything looks like after we do our multiplication and cancel things. Looks quite a bit simpler than where we started. Okay, now we're going to just continue with some algebra here. So let's distribute the a through. That's going to give us ax plus a. Do the same with the b, bx minus b. Okay, and next step is going to seem a little unusual the first time you see it, but we're going to group like terms together. So I'm going to write ax plus bx plus a minus b, and notice that all we did was took the bx and moved it over so that it's together with the ax. Okay, and because these two terms both have an x in them, we can factor an x out. Okay, so I'd like to do that. If we factor an x out of the first two terms, we can rewrite it as a plus b times x plus a minus b. Okay, so we're just doing some algebra to simplify down our equation, basically. Okay, now here comes a step that's going to be a little bit weird. Okay, and it seemed to come out of nowhere, but I'll try to explain the purpose for it. So over on the left-hand side of the equation, I'm going to write in a 0x. Can we get away with doing that? Okay, if you think about it, we can, because 0 times x is just 0, and so we don't change our equation by adding it. But then the question is, why would we want to do such a weird thing like that? Well, it's basically just a way of kind of emphasizing that there are no x's on the left-hand side of our equation. There are no x's. We want to think about this equation that we have as kind of like a balancing beam. We have the same number of x's on the left that we do on the right, and we have the same number of constants on the left as we do on the right. And so what we can say is, let's look at the x terms first, on the left and the right. For this equation to be true, the number of x terms have to balance each other. And so what that means is that the only way that this could be a true statement, a true equal sign, is if the 0 here matches the a plus b here. If those two things were not equal, this couldn't be an equation. And so what we know is that 0 has to be a plus b, has to equal a plus b. Okay, actually, it doesn't really matter, but I think I'm going to write that in the other order. Put the a plus b on the left and the 0 on the right. Okay, that's just telling us that the number of x's on the left have to match the number of x's on the right. Okay, and then we come to the constant terms. For this equation to be balanced, the constant term on the left has to match the constant term on the right. Those two also have to be equal, or this equation is not going to be a true statement. Okay, so that tells us that a minus b has to equal 2. Okay, so we come then to an algebraic situation here. Have you ever seen a problem like this before, maybe in previous math classes? This is what's called a system of equations. We have two equations and two unknowns. The a and the b are our unknowns. How do you solve a system of equations like this? Okay, well, you might remember a couple of ways from algebra. One way is to use what's known as the substitution method, to just take one of the equations and solve it for one of the variables. Okay, I'm going to take the first of the two equations, a plus b equals 0, and just solve it for a. Okay, subtract b from both sides, and that's a equals negative b. And what we can then do is to just take that and substitute into the second equation. All right, we'll do that below. So if a is equal to negative b, we'll go down here and substitute into the second equation. We're going to get negative b minus b equals 2. We just took that a that we had here and substituted in a negative b. Okay, well, notice that negative b minus b is just negative 2b. That just has one variable in it, so we should be able to solve it for b. We divide both sides by negative 2, we're going to get b equals 2 over negative 2 equals negative 1. So we know what b is. We've got one of our two variables nailed down. How do we figure out what a is then? Okay, well, a, we have a formula for that sitting right up here. A is equal to negative b. And we now know that, in a second, let me write that a little bit more neatly. We now know that b is negative 1 from above here, so we'll go ahead and just plug in that negative 1, and we see that a is 1 then. Okay, so we have just solved that system of equations and determined that a is 1 and b is negative 1. Okay, so we've done a lot of work already, and we haven't done our integral yet. Remember that the problem was asking us way at the beginning to do an integral. Okay, let's bring the integral into this problem again. Okay, so what we know then is that if we want to do this integral, instead of integrating the function that we started with, we can integrate its partial fractions decomposition. That's the name for these two pieces that we have here. So basically what happens then is that this integral splits into a over x minus 1. We know that a is 1 plus b over x plus 1. Okay, and I want to emphasize that that equation came from, or that expression came from here, and the 1 and the negative 1 are just the a and the b that we figured out. Okay, we're just filling those in. Okay. And so here's why we did all of this, why it's helpful to have broken this into parts. Okay, notice that we've got a plus sign here. Okay, because of that plus sign, we can take this integral on the right-hand side and to break it into two pieces, 1 over x minus 1 plus negative 1 over x plus 1. So we've taken the integral that we started with and broken it into two smaller pieces. That's why this method is useful. And if we can do those two separate integrals, we're done. Okay, and the nice thing about each of the integrals is we can do both of them with just a nice u substitution. So let's just briefly go through that. If we make u equal to x minus 1, du is equal to dx. And so this first integral turns into just the integral of 1 over u du, which is going to be a natural log. Okay, natural log of the absolute value of u. Okay, I'm going to skip the plus c for a minute, and then ultimately just the ln of x minus 1. Okay, and over to the right, you can go through kind of the same steps, okay, without writing the details of the u substitution. Let me just... You can go through the same type of steps. You've got a minus 1 that you're going to take out, and this is going to turn into just minus ln of the absolute value of x plus 1. Okay, and then we'll put 1 plus c for both of these at the end. Okay, so notice I'm kind of skipping the details of that second u substitution. It's going to work the same as what we did over to the left. And then if you're wondering where this minus sign came from, that came from the negative 1 that's in the top. I just took that and pulled that outside. Okay, and so just rewriting this one more time, we have ourselves an answer to this question. Looks like the natural log of the absolute value of x minus 1 minus the natural log of the absolute value of x plus 1 plus c, and there's our answer. Okay, so there's our first example using the technique of partial fractions. And a question we might ask is, how did we know at the very first step of this problem to break up our fraction into this form? That's a good question that we're going to answer in future videos here.